Here in our webinar platform, you can move our presentation space around to your liking, as well as discover a few new features, such as learning more about your presenter over here, and being able to contact us for any offline discussions you'd like to have over here. My name is Michael Fleischer, and I'm the Americas Marketing and Communications Manager for Megger. I'll be acting as the moderator for today's presentation and assisting with any technical issues or questions for our presenter team. On the side of your screen, you will see an Ask a Question window where you'll be able to enter in any questions you'd like us to answer during our Q&A session at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Louise Beltran, our business manager for LATAM and Canada. To assist with the question and answer session, we also have joining us Abel Gonzalez, Senior Applications Engineer, and Jose Zambrano.
So the agenda for today, we are going to start with the basic concepts. I'm going to turn off my camera to focus on the presentation. Okay, so we are going to start with the basic concepts about the search test. Then we are going to talk about the parameters that we are using as a thresholds. Then we are going to have a little bit of the history of the search test through the years. Then we are going to show you the standards from the past and the actual standards that support the search test. And then we have the summary about all the presentation. So we are going to start with the basic concepts. So what is a search test? So we are doing the search test in order to identify weak insulation or problems about the insulation of the windings. So a search capacitor is connected in parallel to the winding that we are going to test. So we are going to have a sinusoidal oscillation through the winding, and we are going to create a waveform on the screen of the test. So that oscillation has a characteristic shape that is going to tell us what kind of problems we have. So here you can see a graph of different problems of windings during the search test, but this information was used in the past when we don't have the right tools, and we were using only visual tools as information for diagnostic. So the search comparison test finds insulation weakness in coils and windings. These faults are typically turn-to-turn, coil-to-coil, or face-to-face. So let's see the search test many years ago. So here you can see a photograph from an article from Westinghouse in 1951 when they were using the search comparator. This is the same like the search test in order to identify weak insulation on the windings. So, but this idea came from an article published by Rylander in 1926. This article was published in the old IEEE that was called AIEE, the American Institute of Electrical Engineers. So the Westinghouse has started to use this test in 1950 to evaluate winding problems. So the search test can detect weak insulation problems in early stages of insulation breakdown where other tests cannot. So Baker Instrument Company, now we are Megger Baker Instrument, started to manufacture search testers in 1961. So we have a lot of experience about this subject. Let's talk about the dielectric strength of insulation. Why we are doing the search test in any electric motor. So this is an example of low voltage motor. Let's say 480 voltage motor. This is the operating voltage. That means 480 volts. And this is the time through the years. So here we have the very beginning of when the motor started to work. So when we connected the motor, it started to work on the industry, for example. So here, test voltage, 2000 volts. You will see the lines here, different voltages for these vertical lines. These lines represent the transients. So these transients are written in different articles like the IEEE 522. So they are saying when we start up a motor or we have a huge change of the load, or when the motor is working with a VFD, so we will have those transients. So these transients are written in different standards, and that happens in any motor: low voltage, medium voltage, high voltage motor. So the average for this low voltage motor, I'm talking about the transients, the average of the transient voltage are 2000 volts for low voltage motor. That means for this motor, 480 volts, the average is 2000 volts. Then you have here the turn-to-turn insulation of that motor is going, the breakdown of that insulation is at 8000 volts approximately. So through the years, so we have a degradation of the insulation. So the turn-to-turn insulation of the motor is the weakest part of the motor where we can have a problem of, or in other words, is that we will have the very beginning of the problems through the turn-to-turn insulation. So there, through the years, that insulation is going to be reduced. For example, here, at that point, we still have a good insulation in good condition, but we are pretty close to the weak insulation where the arc starts. So the idea to have a predictive maintenance is to identify the weak insulation, or in other words, the arc. And the search test is the only test capable to identify that weak insulation at that level of the voltage. Then, if we cannot identify, or we don't have a search tester, so then the motor or that turn-to-turn insulation is we are going to have a short, maybe in the same coil or between coils, or maybe to the ground, and the motor is going to fail, burn. So the idea of predictive maintenance is to identify that weak insulation through the search test and the modern variables to identify problems on the motor. Now we can identify the problem at this stage. So that means before the arc. And that is a good idea in order to have to identify problems in the motor. So the idea to have the search test started in 1889 with the Paschen law. So this German guy wrote an equation that gives us the breakdown voltage in order to create an arc in certain environment, a gas, a pressure, etc. So this equation predicts the minimum breakdown voltage for a specific pressure and distance. So he identified as a minimum voltage 327 volts between two conductors or two electrodes in order to create an arc. So think about this. In a motor, we have the copper, but we have the insulation. So if we have only two conductors, we need only 327 volts, but because we have the insulation, so we need to have more that 327 volts. And we know that between turn to turn, inside the winding of the motor, we have only 30, 40, 50, or 60 volts only between turn to turn with the copper insulated. So according to this theory, we need to increase the voltage more than 327 volts because we have insulation. So that is the reason we have to increase the voltage over the rated voltage of the motor. And actually, we are sending pulses to the motor. So this is not a continuous DC or AC voltage. No, we are sending DC current voltage, so we can identify the problem in the insulation. Parameters are thresholds. This information is, for most of you, I think this is a new information. I did a survey in the territory that I cover, and 85% of our customers and the people attending webinars, they didn't know that we invented the way in order to have a percentage of error between the waveforms. Yes, it is our patent. In 1989, so Baker Instrument Company, now Mayer Baker Instrument, we filed a patent. What is this about? So in the past, see, our old testers, like ST models, we needed to write two waveforms in order to compare the two waveforms like this one. But in order to identify the problem, we need to match in a visual mode if the two patterns are identical, overlapping. But we didn't have any calculation number or threshold in order to say we have a problem or we do not have a problem. So with this patent, so we created the way that we calculate the percentage of differences of the two waveforms, and we can write that information in our report or the test. So this is our invention. So it started with the D models through the years. So EAR means error area ratio. It's a Baker invention. This is Mayer Baker Instrument. After this patent, I think 5 years, so the patent was opened. Most of the other companies, they try to copy our patent, but our software is our software. It's written in the tester, and nobody can duplicate that software because it is our invention. So for many of you, this is a new information. So this is the EAR, error area ratio. So we are taking, you can see here, the waveform, let's say number 1, and the waveform number 2. So this is the waveform number 1, number 2, and this is the waveform number 1. So because we are sending pulses, again, this is a not steady DC voltage. We are sending pulses of current, DC current, through the circuit. And because this circuit is RLC, so we have a waveform. But because this is a pulse, so the waveform is going to disappear through the time. So we are adding all the points of the first two variables. The first one is the pulse to pulse. I'm pointing here, the pulse to pulse. What is the pulse to pulse? So modern testers, we are increasing, or we are applying current through, let's say, the lead number 1 of the motor, having the lead number 2 and 3 grounded. So the lead number 1 of the motor is receiving the current, so we will have the voltage drop through the circuit, and we are increasing the voltage, let's say, for example, from 1000 to 1050. So we have a waveform at 1000 and the second waveform at 150. Then this is only for the lead number 1. So through the time, the voltage is going to be increased up to the final test voltage. During that time, So the software is going to show you the maximum error post to pulse to the lead number one. So post to pulse, in other words, we are saying EAR post to pulse belongs to each individual lead of the motor. So in that way, we will have pulse to pulse number one, lead number one of the motor, pulse to pulse for the lead number two of the motor, and pulse to pulse for the lead number three of the motor. So we are not comparing waveforms. We are looking only to only one lead during the time the voltage was increased. The second variable is the line to line. So the EAR, error area ratio, line to line. So when we finished rising the voltage for each individual lead of the motor, so we will have three waveforms. So one waveform belongs to the lead number one of the motor when the 2 and 3 was grounded. So then we will have the waveform from the lead number 2 when the lead number 1 and 3 was grounded. And finally, we will have the waveform number 3 when the lead 1 and 2 were grounded. So now, in order to have the line-to-line error, we are going to compare the final waveforms 1 against 2. 2 against EAR was used for the line-to-line error and the pulse-to-pulse error. So this invention, Meyer-Baker invention, was accepted by different entities in the US and worldwide. You can see here, this is an article from IEEE 2011. They are talking about, they created a simulation of the weak insulation in the lab, and they were using our patent, our invention, the calculation EAR, and they were saying that sensitivity of the method was very accurate in order to identify the arc during the weak insulation. This is another article from the ESA organization, EASA, ESA organization from the US, 2016, I think. So they talk about the sensitivity and the good calculation of the error. They took it from our patent. Here you can see, 1992. Then that patent filed in 1989, through the years, we improved the patent, and we call the PPEAR compensation. We were still using the same name, EAR. We didn't change it through the years, but that software on the tester was improved, so that made our tester more a new sensitivity for any search wave change, so we can stop the test anytime when we identify weak insulation. So we are trying to minimize the number of search pulses. So before the invention of the EAR and after the invention. So the ST models, you can see here the waveform, but the operator only have his eyes in order to identify the weak insulation or to match identically two waveforms overlapping. So there were no any calculation in the past before the invention of the EAR. Then we have two different variables as a diagnostic. So then we have line to line and the pulse to pulse for each individual lead of the motor. So better than diagnostic. And this year, 2022, 2 months ago, we released our new EAR Plus trademark. So this is a new software calculation improved from the other tester. So we launched the new ADX. This is the screen of the EAR plus trademark pulse-to-pulse error. So we are the only brand that we can show in real time the error for each individual lead of the motor. So we have here 3 colors. So line 1, 3.5, that means this one, 3.5. So line 2, the pulse-to-pulse, 4.3 here. And then line 3, 1.6, it is here, so the yellow color. So in this way, you have the pulse-to-pulse error and also the line-to-line error, line-to-line error. This information is shown now in our new testers, ADX, in real time. So what is the new tool for diagnostic? Think about this. So this is alarm, 5% for pulse-to-pulse, 5%. And we didn't have any information crossing that threshold. In other words, we have 3.5, 4.3, and 1.6, less than 5%, that 5% was the threshold. But because we have this graph, we can say, okay, the insulation is still in good condition, but we are close to start the weak insulation, because at the time the green graph is going to cross the threshold, then we will identify the arc. So this new concept of diagnostic is going to tell you that the motor is in good condition, can work, but for example, if we are testing the motor in the industry every 6 months, we do not have to wait 6 months in order to do the next maintenance, because we have this information. So the insulation still is in good condition, but we are close to have the arcs. So then we can reduce the time. Maybe in 1, 2, or 3 months, we can do another inspection in order to identify if this information is here. So now we have the arcs, and then we have to remove the motor and send the motor to the shop in order to identify where the arc is presented. So the new error PPEAR plus trademark can tell us if we are close to the electric arc. And also, of course, if we have the electric arc, the tester is going to tell you to. But we can go in advance before the electric arc is presented in real time. So this is our new ADX with the new EAR plus trademark. It's more sensitive compared to the old Baker testers. So let's talk about the surge tests through the years. So again, in the past, we have the ST models where we have to write 2 waveforms at the same time in order to do the comparison, to compare 2 waveforms. So we need to send a current through the lead number 1 and 2, and to have a number 3 grounded. So when we move the knob to the position 2, 3, so we are sending current through the lead number 2 and 3, while number 1 is grounded. If we move the knob to the position TLS 3-1, hot number 1 saying when the rotor is installed on the motor, there's no tool to evaluate the 2 waveforms, if they are identical or no. So we didn't have the software at that time. So only visual evaluation of the waveforms. No automatic stop when there is a weak insulation. So if we have an arc, so the operator must stop the test. So the equipment couldn't do that. We were talking about the ST models, the old ones. Now we will talk about the digital model D series. So now we are having only one waveform at a time, so we didn't have to write two waveforms, only one at a time. Manual mode only, so the waveforms are not the same when the rotor is stalled. So we have the EAR line-to-line on the screen of the tester, but in order to have the information about the pulse-to-pulse error, we needed the desktop software to see the results. No automatic stop when there is a weak insulation, so the operator must stop the test when we have weak insulation. Then we have the model DX, the new generation of the testers. So the same one waveform at a time, manual mode only. Waveforms are not the same when the rotor is stalled. So we have the line-to-line error on the screen here. You can see here the information. And also here we have the pulse-to-pulse error on the screen. So during the search test. And the tester has the capability to stop the test when we identify, or the tester identify, weak insulation. Then we have the model AWA, automatic tester, manual tester at the same time, one waveform at a time. So the waveforms are not the same when the rotor is installed. So we have the line-to-line information here, the pulse-to-pulse information in real time, and this tester stops the test when it identifies weak insulation. And now this year we have the new ADX with a new calculation EAR plus trademark. So the Baker patent was improved. So this is the screen. Here you have the waveform, and in real time we have the pulse-to-pulse error. So here. So one waveform at a time, manual, automatic, and the new sequenced modes. So EAR plus trademark, real time on the screen, EAR plus trademark, pulse-to-pulse on the screen. So when the rotor is installed, we don't have to take the information of the line-to-line. So the new error, PPEAR plus trademark, can tell us if we are close to the electric arc. So this is a new feature comparing to all other Baker testers. So this is a new kind of diagnostic in order to identify the weak insulation. Standards for the search test. I think that there's a microphone open here. So Michael, maybe it's yours. So let's talk about the standards for the search test. So this is so we had different standards for many years. So I started to talk about this guide for preventive maintenance for electric motors, written in 1992, and they were talking about a search comparison test. So for many years, this test was available on the market. So then we have the IEEE 522, the part number 7. They are talking about the maintenance test or test after the installation of machines. So it has different recommendations at different voltages. Then we have the standard IEEE 1415 talking about the search test. By the way, this standard is not active right now, but I'm showing through the years when the standards were talking about the search test. But now we have this is 2010. This is not the updated, but I want to show you that in the past, in 2010, the ISO organization was talking about a search comparison test. The recommendation at that year was to have as a voltage test twice the circuit rating voltage plus 1,000. But this recommendation came from Baker because we invented the patent and we recommended 2 times the rated voltage plus 1,000, and now it's written, that year was written on that standard. Then the same organization, ISA organization, in 2019, there's a recommendation to do the search test for maintenance on the field. And now we have the NFPA 70B. This is a recommended practice for electrical equipment maintenance, 2019. This is updated this year. So here you have an 11.20.4.1 search comparison testing can detect turn-to-turn, coil-to-coil, group-to-group, or face-to-face winding flows that cannot be detected by for low-voltage motors. You are going to apply 2 times the rated voltage plus 1,000. So over 2,300, there's a new formulas calculation for that. So they have a different kind of failures, and they have 5 groups for winding problems. So the inspection could reveal all 5 modems or failures, but the turn-to-turn condition was the initial problem, and the others resulted from that problem. A turn-to-turn failure is usually very difficult to recognize due to the destructive nature of the final fault conditions. So here we can see the importance to have a search test in our industry or more repair shops or service companies. As a summary of this presentation, so the modern variables during the search test are critical for the diagnostic of the winding insulation condition of the electric motor. We can identify weak insulation in early stages, even before the electric arcs between turn-to-turn. That is the new variable. This is the new information of our patent improved. So we have a better variable, modern variable, we call, in order to identify problems of the windings. So in that way, we can reduce the warranties for services during maintenance or repair. This is very useful for more repair shops, because I can say, Mr. Customer, I did the maintenance of your motor, I put it on the furnace, painted, but this information is telling me that we are pretty close to pass the thresholds and we will have arcs on the motors. So, Mr. Customer, if you want to see the real information, maybe we can test your motor in 1 or 2 months again in order to see if we cross the thresholds. For that reason, I'm not going to give you the warranty, because we are close to the arcs. Reliability during the work of the rotating electric machine in the plant. Okay, this is my presentation, a short presentation of the new variables for detecting weak insulation. So now we are going to pass to the questions from the audience.
Excellent. Thanks, Louise. I appreciate you running all of this. Excellent job. Before we jump into our Q&A session, a few quick things. As we jump into our Q&A session, you can also ask any questions that you have that you didn't pose during the presentation over there on the left in the Ask a Question box, and we'll throw it into the order of questions we're about to cover. For those of you that are leaving, please feel free, please fill out our survey over there on the right or as you leave. We really like hearing how we did and what we can do to improve upon our future webinars. On that survey, you can also request a quote or a demo on any Maker products. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be sent to all attendees in 2 business days. Additionally, the link used to join this webinar today will turn into the recording link in about an hour after we conclude here. So with that, we're going to do one last housekeeping thing. If you are interested in seeing any of our past webinars, you can go into our website at us.megger.com/webinars, register for upcoming webinars, or see our library of historic webinars down below. Tomorrow, we're also holding another webinar called Systematic Approach to Testing Power Swing Blocking and Out-of-Step Tripping Elements, which is presented by our panelist here today, Abel Gonzalez. With that, I'm going to throw things over to our panel, if they could join me back here. The first one I'm going to be directing over to Jose Zambrano. So Jose, What is the main difference between EAR and the new EAR plus trademark?
Okay, that is a very important question. Both errors can detect arcs between turns. I mean, with both errors, we can identify weak insulation from turn to turn. But, and this is the important thing to know and the important thing to remember, with the new EAR plus trademark, we can establish, thanks to its high sensitivity, how close we are to the arc before this happens. So we can be much more precise in determining the condition of the insulation between turns. We can anticipate the failure. That is the difference, and that is its great benefits. Back to you, man.
Thanks, Jose. Throwing things next over to Abel. Abel, how often can I perform the surge test on my assets?
Hi, thanks, Mike. That's a good question. Well, basically every time you do maintenance on the asset, when you build the asset, you do the surge test to verify that there are no turn-to-turn failure. The surge test is not a destructive test. Therefore, you can basically run it on the asset anytime you have a maintenance cycle. And it will not lower the life of your asset. You will actually determine whether your asset is in good condition or not.
Isabel?
Yep.
Throwing things over to Luis. How should I use the EAR-PP or the EAR-LL for the analysis of the application?
Okay, so the PP or post-pulse error should be used anytime. I mean, you can use with the rotor is installed on the motor or not, but the line-to-line error, LL, cannot be used when the rotor is installed, because we will have a huge difference in waveform because the effect of the rotor installed. There's another situation too when we have a concentric coils in the special motor where we cannot use the line-to-line error for the calculation. Thanks, Michael.
Thanks, Luis. Back over to Jose. How do you test ground fault for the motor? We just refurbished a new motor, and it failed for ground fault after we installed it, but it passed all the vibration and PM tests.
Okay. In order to determine the condition of the motor's ground insulation system, we must perform what is known as the DC test, which are the MECOM test, the polarization index, or a dielectric absorption test, and the step voltage test. The last one is a high voltage test. Okay, with these three tests, we can have all the necessary information to determine the condition of the insulation to ground. Now, when we use vibration, the vibrations are a very useful tool to determine the mechanical condition of the motor, but they are very limited in being able to precisely establish the electrical condition of the motor. Speaking specifically to the condition of the insulation, we must carry out the static electric test established in the standard for that matter. Back to you, Mike.
Thank you. Next is over to Luis. What are the limits to determine if the insulation system between turns is in good condition?
Well, when we are using the surge test, so there is no standard that talks about the limit, I mean the percentage of the error. So this is something that we can identify on the field. But in our experience, for maintenance practices, we can set the threshold in 5% or 10%. For example, if we have motors on the industry, in the field, that they have a pulse-to-pulse error like 3%. So it doesn't have sense. It doesn't have sense to set the PP error to 10% because most of the models they have only 3%. So we can set the alarm or threshold in 5%. So in that way, we are setting the limits for the thresholds. Thank you, Michael.
Cool. Next is over to Abel. Abel, why is the surge test the only one that can identify turn-to-turn faults?
Well, that's a good question. The reason has to do with the way the voltage is distributed on the winding during the operation of the motor. It is a non-linear distribution of the voltage, especially when transients occurs in the motor, like when there is a motor start or a sudden stop, or when the motor is being operated from a solid state controller. Like Luis was showing, I think in one of his slides, all the spikes that happen during the operation of the motor. In those cases, the voltage distribution and winding is not linear, and the only way we have to simulate that is using the surge test. The surge test will provide the motor with a waveform that's similar in its consequences to the waveform that the motor receives during the start, stops, all the transients that we're talking about. That's why it's the only way you can identify turn-to-turn insulation faults in the motor.
Thanks, Abel. Throwing things back over to Louise. What is the basis of the 10% PPER limit? And if I have a motor at 11%, does it mean that a motor failure is imminent?
As I said, there's no standard for the ER percentage. It's our invention, it's our patent, now improved, but our recommendation is between 5 and 10%. So the key of this information is the trending. So if we are testing a motor for the very first time and I have 10%, so it's something that I think I need to think about. So maybe there's an arc, but if we have more information like the trending, so in the past, for example, that PPER for that lead of the motor was 3%, then 3 months later, 4, then 5, then 7, then 10, so there's a problem. But if we are testing for the very first time, so we need to take a look to different variables. For example, what about the other PP values? Because PP we have for the lead number 1, then lead number 2, and lead number 3. Are the 3 values the same? 10%, 11%? Or only one lead 10% or 11% and the other 2%? So it's a huge difference. So there's a problem in the model. So these are the considerations to take during the evaluation of the model. Thank you.
Our next question I'm going to throw over to Jose. What would be the largest generator I could use on the new tester?
Okay. With our largest ADX, it would be 15 kV. We can test 5,000 HP machine or 3,750 kilowatts. So this number are calculated on a 4-poles machine, and when we are doing the test in the junction box. So if the condition of the test are different, maybe this number that we say before maybe change. So this is a very important thing to know, because we have to be sure that our equipment, our device can do the test in the machine.
So I would like to add something else, Jose. So
okay.
In the near future, the new ADX is going to work together with the Power Pack PPX. So working together with the new ADX and the Power Pack, we will be able to test huge generators close to 100 megawatts. So it's a combination of the ADX within the near future with the Power Pack PPX. Thank you, Michael.
Thank you both. And lastly, we have a question for Abel. Can a search test be done from the circuit breaker instead of motor leads? And are there any differences in the accuracy of the results?
Well, like any insulation test, the more elements that you add in series with the device that you're testing, the more capacitance that you're adding, and therefore you need a larger machine, right? That said, yes, you can do the test from the circuit breaker, as long as the circuit breaker is insulated. However, when you find a problem, what's happening is that you're going to start questioning yourself, like I've seen happen. Oh, I'm doing it from here because it's easier, and then no, I got in trouble. Where is the problem? Then you start breaking the problem into pieces. So the question is yes. I mean, the answer is yes. Just know that there are many plus and minuses to doing it that way.
All right, thanks, Abel. It looks like those are the questions that we're going to be handling here live today. If you have any questions that we didn't answer here live, or you'd like to come up with a completely new question that you'd like to come up with later, feel free to drop us an email over at broadcast@megger.com or fill out our contact form there on the right. And be sure to fill out our survey so we know how we did, and how we can continue to improve upon our future webinars. And if you'd like to get a quote request going towards us so we can reach out to you in a little bit. But as a reminder, everyone here is going to get a copy of the presentation, a certificate of attendance, and a link to the video recording of this webinar in 2 business days. With that, I'm going to thank everyone in attendance for joining us today. And if you could, please feel free to join us tomorrow for our webinar at 10 a.m. Central Time, a systematic approach to testing power swing blocking and out-of-step tripping elements, which is going to be presented by Abel here. So if you haven't gotten enough of us today, we can see you tomorrow. But with that, I'm going to sign off and wish everyone a great day. And if I don't see you tomorrow, a great weekend. Bye, guys.
Thank you. Bye-bye.
Bye-bye. Thank you.